This is the ninth topic in the Probability and Stochastic Processes course, in which we are going to talk about the classification of Markov chains states. In the previous topic, we were introduced to discrete time Markov chains and one way of analyzing discrete time Markov chain, namely by transient analysis. In transient analysis, we are looking at a particular Markov chain at a particular time, say at time n, and we would like to know the state occupancy probability, namely with what probability is the DTMC is in a particular state at time n. This is what we call the transient analysis. Now, another analysis that is common to Markov chains is the so-called the steady state analysis. Now, the steady state analysis looks at the Markov chain in the long run. So after we execute it or we run it for a long time, or after the Markov chain has already reached the steady state or an equilibrium in which there is no changes anymore in its state occupancy. For this kind of analysis, we need to classify the state because not all Markov chain has this long-term probability. The existence of this long-term probability depends on the states of the Markov chains. So that is the reason why we have to classify the states of Markov chains. So let's start. The first fact that you're going to see is about accessibility or reachability. A state J is called accessible or reachable from state I if the n-step probability Rijn is more than 0 for some n. So that means that there is a transition indeed from state I to state J. There is a way to go from state I to state J within n steps, and it happens with a probability that is non-zero. So the probability of the path, we have already seen in the previous topic about the probability of path. Probability of a path, there is a path, and the probability of this path from I to J is more than 0, is non-zero. Now, this is called accessible or reachable. In graph, we usually call this connected. So we see the correspondence between connectedness and reachability or accessibility in Markov chain. Yeah, so this state J is called reachable from state I if we can find an n-step probability Ijn which is more than 0 for some n. Now let Ai be the set of all states that are accessible from state I. So that means that all reachable state from I is called Ai. Okay. Now, the second fact is that a state I is called recurrent if for each state J accessible from state I, then state I is also accessible from state J. So that means that if J can be reached from I, then I can also be reached from J. So they are recurrent. That means that if somehow we transition in several steps from I to J, then later on we will be going back again to state I. Or if we want to describe this, to express this in a more formal way, then this is just the same as saying that for all J element of Ai, then I is also element of Aj. So you see, they are back and forth. If J is an element of Ai, namely J is accessible from I, then also I is an element of Aj. I is also accessible from J. Now, intuitively, this simply means that that's why we call it recurrent. A state is recurrent if visiting it once means that it can be visited infinitely many times. If we have already visited once in the state, in a set that are recurrent, yeah, if it is recurrent, then that means that we can always visit it again and again and again ad infinitum. That's the second fact. Now the third fact is the opposite of recurrent. The opposite of recurrent is called transient. A state I is called transient if it is not recurrent. Namely, that there is a state J, which is an element of AI and accessible from I, such that state I is not accessible from J. So J is accessible from I, but I is no longer accessible from J. So that means that if we were originally from I and we happen to go to J, then we escape. We can no longer go back to I. This is what we call a transient state. So state I is called transient then, because there is a possibility for us to escape from this state. There is a possibility for us to go out of this. Therefore, a transient state can only be visited finitely often, because once we escape, then we can no longer visit it. Okay. Let's continue with the fourth fact. If state I is recurrent, then AI is called a recurrent class. So that means that every state that can be reached from I is called a recurrent class. So if we know that state I is recurrent, then every state that can be reached from that state is called a recurrent class. And it is not actually that difficult to prove that this recurrent class is an equivalence relation. Yeah? So that means that if J is inside of this AI, and we already know that state I is recurrent, then state J must also be recurrent. There is no other way, because they form an equivalence relation. Fact number 5. If a recurrent class is called periodic if its states can be grouped into D, which is larger than 1. So that means that at least 2 disjoint groups S1, S2, and so forth until SD, such that all transition from one group brings us to the next group. Look at this. So there is a particular pattern in the occurrence of these states. So a recurrent class is called periodic. Remember again that we have a recurrent class is a set of class, and they form basically an equivalence relation. Now this group of recurrent class, this group of states is called periodic. The whole thing is called periodic if inside of it the state can be grouped into D, which is larger than 1. D larger than 1 means at least 2. Yeah? So this means at least 2. 2 disjoint group. If it is only 1, then it is not periodic. At least 2 groups, S1, S2, and so forth until SD, such that all transition from one group brings us to the next. I mean, this will going to be clearer if we see the formal way to describe it. If I is an element of Sk and Pij is larger than 0, so it happens with probability, with a positive probability, then J, pay attention to this one, then J must be an element of Sk plus 1 if k is equal to 1, 2, and so forth until D minus 1, or S1. So that means that if this is the set of states S1, S2, S3, and so forth until SD, and we have here a set of transitions from this group, state of transition from that group, we can do this. So we can group this recurrent class into this form. And the last one from SD is going back here to S1. That's what it means. So if I is an element of SK, if I is an element of one of these set of states and Pij is larger than 0, then there are only two possibilities. Namely, the first one, yeah, J is an element of Sk plus 1. If K is equal to 1, 2, 3 and so forth until D minus 1, or S1 if K is equal to D. So this is what we call a periodic. And look at this. The period, the smallest period, of course, is equal to 2 because if it is 1, it is not called periodic. And the last fact is called aperiodic. A recurrent class is called aperiodic if it is not periodic. Look at this. This is still a recurrent class, but it is not periodic. That's why we call it aperiodic. It is still, yeah, a recurrent class. Therefore, in this case, D is exactly equal to 1. So the whole class is in one period. Yeah, the whole class, the whole set of states is in one period. So if this is the case, then there must be a time n such that Ijn is larger than 0 for all I and j element of the state space. So that means that you can take any state, any two state, there must be time n such that the probability of transitioning from one state to another within n transition, the probability of the path from them is larger than 0. Now we have these 6 definitions, 6 facts or 6 definitions that we will be used later on to describe the what do you call this, the steady state analysis. Okay, we're going to use this. Now this is going to be used in steady state analysis of DTMCs. And actually, this classification of state is not only for DTMCs but also for continuous time Markov chains. What is this steady state analysis? Steady state analysis computes the steady state distribution, namely the distribution of the Markov chain once it enters an equilibrium. An equilibrium means that that once we run the DTMC, it enters an equilibrium in which the changes of states inside when it is run is no longer happening. Yeah, so we can see it that way. But also, actually, we can see this as a long-term state occupancy. What does it mean? It means that when we run the DTMC for a long time, for a long horizon, for example, for a long time, closer to infinity, for example, and we would like to know the portion of this particular time, this running time that we spend in particular state, this is also actually the same. These two things are the same. The steady state analysis compute these two things at the same time. Yeah. So this is what we call, this view is called the long-term state occupancy. So it's steady state distribution, or you can also view it as a long-term state occupancy. Remember again Rijn, namely the probability of starting at state I and ending at state j after n transition. Now, this long-term state occupancy or steady state distribution can be achieved by computing this Rijn when n is large. Large means that it is closer, it is approaching infinity. So we have this theorem, the steady state convergence theorem. But not every discrete time Markov chain has this steady state distribution or long-term state occupancy. Yeah, we have this only for specific cases. And aperiodic, look at this. So one of the conditions is aperiodic Markov chain with a single recurrent class satisfies the following property. So that's it. Yeah, so the condition is we have to have an aperiodic Markov chain with a single recurrent class satisfies the following properties. For the first one, for each state j, the limit of Rijn when as n approaches infinity must be equal to some probability, is an exact probability. Namely, we just call this pi j. Look, we usually use pi to denote the state occupancy probability, but at a particular time. Now we take out the time because we think that this happens after infinity or once it is stationary. So pi j is the probability of xn is equal to j when n is large and is already stationary, or we are already in an equilibrium. That's the first property. The second property is this pi j is a unique solution of this system of linear equation. What is that? Pi j is equal to the sum of k is equal to 1 until m pi k multiplied by pi kj, for j is equal to 1, 2 until m, and the sum of this pi j, for of course this is j, is equal to 1. So if you sum all the possibility of this pi j, this will be equal to 1. So this is the normalizing factor basically. Yeah. So this is a system of linear equation. But if you look at this system of linear equation, you will see that this is actually a vector matrix multiplication. Yeah, because this is a vector and this is a matrix. Yeah. So therefore, we can describe this for the discrete time Markov chain as vector pi is equal to vector pi multiplied by p. The vector of pi consists of pi 1, pi 2, and so on until pi m is the stationary probability distribution, which form a vector, so that we call this a stationary probability vector. Yeah. So therefore, to do steady-state analysis, if it exists, the steady-state analysis result in the unique solution of this system of linear equation. And the third property is that pi j must be equal to 0 for each transient state, and pi j must be more than 0. It is non-zero for each recurrent state. This is the end of our topic about the classification of Markov chain state.